In late 2025, something appeared in the data, not a signal in the way science fiction imagines it, but a candidate event that passed the first level of scrutiny. A small cluster of radio features, narrowband and persistent, showed up during targeted observations of 3I Atlas, the third confirmed interstellar object ever recorded passing through our solar system. The confusion wasn't about alien intelligence. It was about the methodology itself. When you point a sensitive radio telescope at a moving target traveling at hyperbolic velocity on an unbound trajectory, and a feature appears that seems to track with that motion, you must treat it seriously. Not because you believe it, because you must disprove it. This is the uncomfortable edge where data collection meets interpretation, where a signal can appear to originate near an interstellar visitor, where the same observing architecture designed to find anomalies is engineered to destroy them. On December 19, 2025, as 3I Atlas reached its closest approach to Earth at 1.7 astronomical units, 167 million miles away, the largest steerable radio telescope on the planet was pointed directly at it, sweeping frequencies from 1 to 12 GHz. Within that flood of data, analysts found what they expected: thousands of narrowband hits, most attributable to terrestrial sources, satellites, ground stations, the electromagnetic hum of human civilization, bleeding into the search. But a handful survived initial filtering. They drifted in frequency the way a signal from a distant, moving object should drift. They appeared strongest when the telescope pointed at 3I Atlas, weaker when pointed away. For a moment, they looked real. This is where we begin, not with certainty, not with spectacle, but with the discipline required to untangle interference from implication. Because in radio astronomy, what appears to be near a target is often nowhere near it at all. The question isn't whether we heard something. It's whether we understand what we're listening to. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System facility in Rio Hurtado, Chile, flagged an object moving through the southern sky. Within hours, orbit calculations confirmed what initial observations suggested: hyperbolic trajectory, eccentricity exceeding 6, origin beyond the solar system. This was not debris from the Kuiper belt. This was not a long-period comet making a routine pass. This was 3I Atlas interstellar comet, the third such visitor ever confirmed. Pre-discovery images traced it back 55 days, enough to refine the trajectory, but not enough to eliminate uncertainty about its nature. It appeared red in early images. Spectroscopy detected cometary volatiles. By October, as it approached perihelion at approximately 1.4 astronomical units from the Sun, a visible coma developed. Water ice breaking down under solar radiation, releasing hydroxyl molecules that radio telescopes could detect as natural emission lines at 1600 MHz T. But within days of discovery, another kind of observation had already begun. The Allen Telescope Array in Hat Creek, California, locked onto 3I Atlas on July 2nd, less than 24 hours after the initial announcement. Not because anyone expected technology, because the statistical rarity of interstellar objects demands thoroughness. Because if we do not look, we cannot rule anything out. The search covered 1 to 9 GHz, a range broad enough to capture both terrestrial interference and hypothetical narrowband transmissions from an object moving at 32 kilometers per second relative to the Sun. The sensitivity reached down to 10 watts of equivalent isotropic radiated power at the low end, escalating to over 100 watts at higher frequencies, meaning if something on or near 3I Atlas were transmitting with the power of a household light bulb, the array could detect it. 7.25 hours of observation. 74 million narrowband hits recorded by the detection pipeline. Most were immediate rejections. GPS downlink frequencies, iridium satellite bands, fixed satellite allocations, the dense spectral clutter of L-band, where human telecommunications saturate the sky. 16% of the observed bandwidth was so contaminated it had to be blanked entirely. Every hit within those ranges discarded without further analysis. The remaining candidates were filtered by drift rate, frequency change over time, the Doppler signature expected from relative motion between transmitter and receiver. For 3I Atlas, that drift fell within a narrow envelope, 0.05 to 1.5 Hz per second across the search range, accounting for Earth's rotation, the telescope's motion, and the comet's trajectory through space. After blanking, after drift filtering, after spatial localization using a two-beam strategy, where one beam pointed at 3i Atlas and another pointed 5 beam widths away to test whether signals stayed locked to the target or followed the telescope. After all of that, 211 events remained for visual inspection. Every one resolved into interference. Satellite transmissions, mimicking point sources. Modulated signals from terrestrial allocations. Broadband features, misidentified as narrowband by the initial algorithm. Not a single candidate survived the full sequence of rejection tests. But here is the trap. The fact that candidates appeared at all, even temporarily, means the system is working as designed. A sensitive search will produce false positives. It must, or it isn't sensitive enough. The Allen Telescope Array was not looking for proof. It was setting limits. And those limits, 10 to 110 watts across the frequency range, became the first constraint on artificial radio emission from an interstellar object discovered in 2025. The investigation did not end in July. It unfolded across months, across telescopes, across hemispheres. In late November, the Meerkat Array in South Africa observed 3i Atlas at frequencies between 900 and 1670 MHz, detecting natural hydroxyl emission from cometary outgassing, exactly what solar heating and ice sublimation predict, while the Breakthrough Listen backend searched the same data for technosignatures. Sensitivity reached 0.17 watts, roughly the output of a mobile phone handset at the comet's distance. No artificial emission. The Parkes Observatory in Australia recorded sessions in July, September, and October, with the final observation on October 5, achieving sensitivity to transmitters around 5 watts. Narrowband analysis is still ongoing. The Vera Rubin Observatory contributed optical monitoring, searching for transient laser signals in visible wavelengths, while constraining the object's albedo and rotational properties. And then came December. As 3i Atlas emerged from behind the Sun, after months of solar conjunction, observatories prepared for closest approach. NASA had noted in September that the object would become difficult to observe due to proximity to the solar glare, then reappear in early December for a final observing window, before it moved too far from Earth to study in detail. On December 18, 2025, less than 24 hours before closest approach, the Robert C. Byrd Green Bank Telescope, 100 meters in diameter, the largest fully steerable single-dish radio instrument in the world, conducted a 5-hour observation using 4 receivers spanning 1 to 12 gigahertz. At this distance, 1.7 astronomical units, the sensitivity reached approximately 0.1 watts, lower than any previous search. Sensitive enough to detect transmissions weaker than a standard terrestrial walkie-talkie, if they existed. The data were processed using the same pipeline deployed at the Allen Telescope Array: narrowband hit detection, spatial filtering, drift rate analysis, visual inspection. The result, published in a technical note on December 20th, was methodical and unambiguous. No candidate technosignatures. No signals localized to 3i Atlas that could not be attributed to terrestrial or satellite sources. The conclusion, delivered without fanfare, was that 3i Atlas continues to behave as expected from natural astrophysical processes across all observed wavelengths and timescales. So why did candidates appear at all? Why does a signal seem to be near an interstellar comet when it isn't? The answer lies in how radio telescopes discriminate between sources. A narrowband signal is efficient for communication. Concentrated energy in a thin slice of spectrum, easy to distinguish from broadband natural emission. Doppler drift is the signature of motion. As a transmitter moves relative to the receiver, the observed frequency shifts predictably. For a ground-based radio telescope, observing a fast-moving interstellar object, the expected drift depends on several contributions: the object's velocity through space, Earth's orbital motion around the Sun, Earth's rotation, even the slight tumbling or rotation of the object itself. All of these add up. And here's the problem. A terrestrial transmitter, stationary on Earth or aboard a satellite, also experiences Doppler drift relative to the telescope due to Earth's rotation. If that drift happens to fall within the range expected for 3 Atlas, the signal will pass the first filter. It will look briefly like it could be associated with the target. This is why follow-up is essential. The discipline that finds a candidate is the same discipline that destroys it. You observe again. You point the telescope slightly off target and check whether the signal persists. You compare the signal's behavior across multiple beams. You cross-reference the frequency against databases of known transmitters, satellite allocations, radar systems. You measure whether the signal tracks the object's changing velocity or remains locked to Earth's reference frame. Most candidates collapse under this scrutiny. They are revealed as interference, artifacts, the noise floor of a technologically saturated planet. The few that survive become targets for even more rigorous testing. None, so far, have passed all tests for 3I Atlas. But what does that non-detection mean? What can you learn from silence? In technosignature science, absence of evidence is not worthless. It is a measurement. It defines what the object is not. The reported upper limits, 0.1 watts at Green Bank, 0.17 watts at Meerkat, 10 to 110 watts at Allen Telescope Array across broader frequency ranges, constrain the power of any hypothetical transmitter on or near 3 Atlas. These are not speculative numbers. They are derived from instrument sensitivity, observing time, distance, and the signal processing methods used to search the data. They place 3A Atlas within a map of ruled-out possibilities, tightening the parameter space for what interstellar objects might carry in terms of artificial radio emission. The physics of the comet supports this conclusion. 3I Atlas reached perihelion on October 29, 2025, at approximately 1.36 astronomical units from the Sun. At that distance, solar heating drives sublimation of volatile ices, water, carbon monoxide, carbon dioxide, producing the coma and tail observed in visible wavelengths, and the hydroxyl emission detected in radio. This is exactly what you expect from a natural comet. The activity correlates with solar distance. The spectrum matches complementary chemistry. The trajectory, while hyperbolic, shows no anomalous accelerations beyond what outgassing predicts. Small non-gravitational forces caused by jets of gas pushing asymmetrically as the surface heats. If there were a transmitter aboard, it would have to be passive, unpowered, or operating outside the surveyed frequency and power ranges. None of these scenarios are physically impossible, but they require assumptions beyond what the data demand. And so the investigation reaches its natural endpoint. 3 Atlas, as far as current observations can determine, is a comet. An interstellar comet, following an unbound trajectory, carrying the chemical signatures of a distant stellar nursery, passing through our solar system on a path it will never retrace. It is loud in natural radio emission, hydroxyl lines bright enough for Meerkat to detect across millions of kilometers, but radio quiet in the engineered sense. It does not transmit. It does not respond. It outgasses, rotates, and recedes. Yet the mystery does not vanish. It transforms. Because even a null result carries weight when the target is this rare. Only 3 interstellar objects have been confirmed. Oumuamua in 2017, Tuta Borisov in 2019, and now 3 Atlas in 2025. Each discovery refines our understanding of how often such visitors pass through, how detectable they are, what kinds of observatories can spot them before they fade back into the dark. Each null result in technosignature searches becomes part of a statistical record. How many interstellar objects have been thoroughly searched, across what frequency ranges, with what sensitivity? The absence of detections does not prove that no interstellar probes exist. It proves that if they do, they are either rare, inactive, operating in ways we have not yet tested, or passing through regions we are not yet monitoring. What remains unanswered is not whether 3I Atlas carried technology. It's how many other interstellar objects pass through the solar system unnoticed each year. Current models suggest dozens to hundreds, depending on size and activity. Most would be too small, too dark, or moving too fast to catch with existing surveys. 3IA Atlas was discovered because it brightened as it approached the sun, because it developed a coma, because Atlas and other survey telescopes are optimized to find moving objects against the static background of stars. But an inactive object, no outgassing, no tail, no change in brightness, could pass within Earth's orbit and never trigger an alert. This is the edge of observational completeness. What we see depends not just on what's there, but on whether our instruments are looking in the right way at the right time. Future surveys will push deeper. The Vera Rubin Observatory, now in commissioning, will scan the sky repeatedly with unprecedented sensitivity, detecting fainter and faster moving objects than any previous system. The next generation of radio telescopes, next generation Very Large Array, Square Kilometer Array, will extend technosignature searches to frequencies and sensitivities beyond what current instruments can achieve. And the next interstellar visitor, whenever it arrives, will be observed with the lessons learned from Oumuamua, Borisov, and Atlas. Start early, observe across wavelengths, coordinate globally, and accept that the most interesting discoveries often come not from what you detect, but from what you systematically rule out. There is a kind of humility required here. The humility to admit that a strange signal, briefly compelling, can resolve into terrestrial noise and still be worth investigating. The humility to understand that sensitivity and interference coexist, that every increase in our ability to detect faint signals also increases our vulnerability to false positives. The humility to recognize that an interstellar object, carrying the chemical fingerprint of another star system, is already extraordinary without needing to carry technology. We search because searching is how we learn what the universe contains. We set limits because limits are data. And we wait, instruments ready, for the next visitor to cross the threshold between interstellar space and the mapped territory of our solar system. 3I Atlas is now receding. Its closest approach is past. The observing windows are closing as it moves farther from Earth and Sun, fainter with each passing month. But the data remain: 7 hours from Allen Telescope Array, 5 hours from Green Bank, multiple sessions from Parkes and Meerkat, optical monitoring from Rubin and other facilities. All of it publicly archived, available for reanalysis, part of a growing library of observations that define not just what 3 Atlas is, but what class of objects it belongs to, how interstellar comets behave, and what kinds of signals they do not produce. The unknown signal that appeared in the data was never unknown in the conspiratorial sense. It was unknown in the technical sense, a candidate that required identification. And once identified, once traced back to its terrestrial origin, it stopped being a mystery and became a lesson in how careful science separates meaning from noise. This is the kind of mystery science keeps. Not the unsolved riddle, but the rigorously examined question that yields to evidence. Not the tantalizing hint of something more, but the disciplined acceptance that absence of detection, when conducted with sufficient sensitivity and thoroughness, is itself an answer. 3A Atlas came from another star. It passed through our solar system, bright enough and active enough to study, and it carried no detectable artificial radio emission down to power levels equivalent to handheld transmitters. That statement is not a disappointment. It is a measurement. And measurements, accumulated across objects and time, are how we map the distribution of natural and artificial phenomena in the cosmos. The next interstellar object is already on its way, somewhere in the dark between stars. When it arrives, we will point our telescopes toward it, sweep through frequencies, search for narrowband drifts and spatial localization, and once again confront the same question: what is this, and how do we know? The answer will come not from a single observation, but from the patient, methodical application of tests designed to distinguish signal from interference, anomaly from artifact, the genuinely strange from the merely unexpected. And if, someday, a candidate survives all those tests, if a signal appears that tracks perfectly with an interstellar object, persists across multiple observations, shows characteristics inconsistent with any terrestrial or satellite source, then the investigation will deepen, not end. Because extraordinary claims require extraordinary evidence, and the burden of proof in technosignature science is absolute. Until then, we continue. We observe. We constrain. We document the silence alongside the noise, knowing that each null result narrows the space where undiscovered phenomena might hide. And we hold the right kind of quiet, not certainty, not fear, not the disappointment of anticlimax, just the measured readiness for the next strange dataset, the next interstellar visitor, the next moment when an unknown signal shows up in the data, and an unknown signal shows up in the data, and that the slow, careful work of understanding begins again.